Following on from basic aerodynamic theory, this lesson on subsonic airflow will cover the principal definitions and terminology concerning aerofoils and the airflow around them, and how changes in airflow affect the resultant forces. The aerofoil can be defined as a shape capable of producing lift with relatively high efficiency. As air flows over an aerofoil at a sufficient speed, it will have certain effects on the static pressure surrounding the aerofoil, as propounded by the principle of continuity and Bernoulli's theorem in the last lesson. Even before the airflow reaches the aerofoil, the pressure drop over the upper surface will cause the flow to rise towards it. This is known as upwash. At a point on the lower side of the leading edge, the airflow will be brought to a halt at a point called the stagnation point, where the airflow separates to pass over or under the wing. As the air flows back over the aerofoil, it will tend to slow down in accordance with the basic principles, flowing against the adverse pressure gradient as the higher pressure air below the aerofoil tries to go from high to low pressure, that is, forward from the trailing edge to the low pressure area on top. The pressure distribution is shown here, with the highest pressure concentrated around the stagnation point and the low pressure extending up and forward to a peak above the aerofoil, with the pressure differential creating the lift force indicated. Also shown is the force, drag, which acts against the forward movement of a wing and is caused partly by the lift itself. Lift and drag are fully covered in subsequent lessons in the syllabus. Having introduced the basic characteristics of the airflow around an aerofoil, we shall now look at the terminology and definitions associated with aerofoils. The chord line is a straight line joining the centres of curvature of the leading and trailing edges of an aerofoil. The chord is the distance between the leading and trailing edges, measured along the chord line. The angle of incidence is the angle between the wing root chord line and the longitudinal axis of the aircraft. This is fixed for the wing, but may be variable for the tailplane. The mean camber line, also known as the mean line or camber line, is a line joining the leading and trailing edges equidistant from the upper and lower surfaces. Maximum camber is the greatest distance of the mean camber line from the chord line, and is expressed as a percentage of the chord, and its location along the chord line as a percentage of the chord measured from the leading edge. When the camber line is above the chord line, the aerofoil is said to have positive camber, and when it is below, negative camber. A symmetrical aerofoil has no camber, as chord and camber lines are coincident. Thickness-chord ratio is the maximum thickness or depth of an aerofoil section, expressed as a percentage of the chord from the leading edge. The thickness and thickness distribution of an aerofoil section have a significant effect on its airflow characteristics. Leading edge radius is the radius of the curvature of the leading edge, which can significantly affect the initial airflow characteristics of the aerofoil. Basically, the smaller the radius, the sharper the leading edge. Relative airflow, or relative wind, or free stream flow, is the direction of the airflow produced by the movement of the aircraft through the air, and has three characteristics. First, its direction is opposite and parallel to the flight path, which is the direction taken by the centre of gravity. The aircraft's attitude is not a factor. Secondly, its condition is that it is air close to but unaffected by the presence of the aircraft. That is, its temperature, pressure and velocity are not changed by the aircraft's passage through it. Thirdly, the relative airflow's magnitude is the speed of the aircraft through the air, the true airspeed. If the airflow does not possess all of these three characteristics, it is referred to as effective airflow. Total reaction is the resultant of all the forces acting on the aerofoil section. namely lift and drag. The centre of pressure, or CP, is the point on the chord line through which lift is considered to act. Lift is the aerodynamic force generated by the aerofoil, which acts at 90 degrees to the relative airflow. Drag is the aerodynamic force which acts parallel to and in the same direction as the relative airflow, that is, opposite to the flight path. Angle of attack is the angle between the chord line and the relative airflow. It is often referred to as alpha, written as the Greek letter. An alternative, but less used term is aerodynamic incidence. The angle of attack between the chord line and the effective airflow is referred to as the effective angle of attack. When we are considering airflow velocity, it makes no difference to the pressure pattern created by the flow over an aerofoil if the aircraft is moving through the air or the air is moving over the aircraft. It is the relative velocity which is the most important factor. For example, an aircraft flying level at 80 knots will produce about the same lift as it would stationary on the ground, facing into an 80-knot wind, depending on angle of attack. To promote full understanding, we will be referring to both situations, either where air flows over a wind tunnel model, or aircraft in flight moving through stationary air. Three-dimensional airflow is the true airflow over an aircraft and consists of a two-dimensional flow, modified by various pressure differentials. This will be examined later in the syllabus. For now, we will consider two-dimensional airflow. Two-dimensional airflow assumes a wing with the same aerofoil section along its entire span, with no span-wise pressure differential or flow. This concept is used to illustrate the basic principles of the generation of aerodynamic force. As air flows towards an aerofoil, it will be turned upwards towards the lower pressure over the upper surface. This is termed upwash. After passing over the aerofoil, the flow returns to its original flow level and state. This is termed downwash. On the screen, you can see an aerofoil at a representative angle of attack, subject to a given dynamic pressure or IAS. The pressure distribution showing that if the static pressure on one side of a body is reduced more than on the other side, a pressure differential will exist. If the same angle of attack is maintained, and the IAS, and thus the dynamic pressure, is increased, the pressure differential will increase. The pressure differential acting on the surface area will produce an upward acting force. So, if dynamic pressure increases, the upwards force increases. At a constant dynamic pressure, increasing the angle of attack, or alpha, will also increase the pressure differential, but will also alter its distribution pattern. The aerofoil profile presented to the airflow will determine the distribution of velocity change, and hence the pressure pattern over the surface. This pattern is determined by the aerofoil's geometry, that is, the thickness and its distribution, which are fixed, the camber and its distribution, which are assumed to be fixed for now, and by the alpha, which is variable. The greatest positive pressure occurs at the stagnation point, where the relative flow velocity is 0. This point is somewhere near the leading edge. As the alpha increases from -4, it moves from the upper surface around the leading edge to the lower surface. The stagnation point is where the airflow divides over the upper and lower surfaces, and pressure here is static plus dynamic. The flow over the top accelerates rapidly around the leading edge and over the front portion of the wing, creating a substantial static pressure drop. The rate of acceleration increases with alpha, up to about 16 degrees. The pressure reduces continuously from stagnation value, through free stream pressure, to a position on the top surface where a peak value is reached. From there, the airflow decelerates progressively, and the pressure rises back to free stream near the trailing edge. It should be noted that any imperfections on the upper leading edge surface, such as dents, dirt and insects, ice or frost, etc., can seriously disrupt the flow acceleration in this critical area. At alphas less than 8 degrees, the underside flow is much less accelerated and reduces pressure to only a small negative value. The pressure differential between the stagnation point and the lower pressure at the trailing edge creates a backwards acting force called form or pressure drag, which is covered later in the syllabus.